Okay, folks, let's go over the sample exam. All right, so what's not on the sample exam are some nomenclature questions. They're like what they were in the textbook from chapter 4 and 5. So FYI. Let's go ahead and let's talk about these and how we're going to approach these. There's a couple of different ways you can approach these. Some of you guys have a hard time comparing chairs and cyclohexagons. Hexagons, I guess. And so one of the things you can do, there's more than one way to approach this. You can see that this methyl group is going up and this ethyl group is going up. Over here, the methyl group is going up, and over here, the methyl group is going down. So if there's one is up, and the other one's up, down, by definition, okay, they can't be the same compound, right? Because they're locked. There's no free rotation. They can't be enantiomers because, you know, they wouldn't be mirror images. They're obviously a little bit more than constitutional isomers because it's 1-ethyl, 2-methyl for both of these, cyclohexane. Okay, and so again, if I were to convert this chair to a cyclohexane, my methyl would be up and my ethyl would be up. Okay, you can go so far as to assign stereoisomer, stereogenic centers rather, absolute configuration, R or S. You cannot assign R and S though, unless you have it in the cyclohexane form. Okay, so moving on, obviously these guys are what? They would be diastereomers. Okay. The next one. Okay. So obviously, again, they're more than constitutional isomers because it's 1 amino, 2 hydroxyl. Okay, so 1, 2, and both of these, they're both on cyclopentyl rings. Okay, and this does take some imagination, but if I were to flip over the second one, it would be a perfect mirror image. So they're enantiomers. For those of you that cannot see that, if I were to look at this stereogenic center, assign priority 1, 2, 3, this would be R. Look at this stereogenic center, assign priority 1, 2, 3. This would be S. Come over here, do the same thing. Okay, 1, 2, 3. Okay, it's clockwise, but it's going behind, right? The H is coming out. So this would be what? S. Same thing down here. Okay, 1, 2, 3. Again, counterclockwise, but again, the H is coming out. So I flip this. Okay, and so what we also see is these absolute configurations are exactly the opposite. The amino on one is R, the amino on the other one is S, and the same thing with the OH. S on the first, R on the second. So they are enantiomers. All right. Okay, so this next one. Again, there's more than one way to approach this. I'm going to show you how I would approach this. First thing I'm going to do is I'm going to find my longest carbon chain, okay, which is 1, 2, 3, 4. Okay, I'm going to do the exact same thing on the second carbon. Okay, so there's 1, 2, 3 for the carbon behind, and then 4. Okay, so they both are forward carbon chains. This aldehyde is this aldehyde. Okay, this OH is this OH, and this H is this H. So far, so good. I go around on the back side. This OH is this OH. This CH2OH is this CO2OH. Ah, but what I have here is I have what? Here I have a hydrogen, and here I have a methyl. Okay, so they're not the same. The compound on the left has 1 additional carbon. So then by definition, they can't be constitutional isomers. So the answer would be no relationship. The next one is you can count up the carbons and you can count up all the hydrogens. I'm going to teach you something called degrees of unsaturation on Tuesday. And what we can see here is both of these have 2 degrees of unsaturation. I'm sorry, both of them have 1 degree of unsaturation. My bad. And which means 1, 2, 3, 4, 5, 6, 7. So they both have C7H14. If this is 1, 2, 3, 4, 5, 6, 7. Okay. And so this is a shortcut. If they have 7 carbons and only hydrogens, if they have the same number of carbons and they have the same number of degrees of unsaturation and they're just hydrocarbons, then by definition, they have to have the same molecular formula. Okay. And you can go ahead and you can count these up. Obviously, these are not stereoisomers. Okay. These are constitutional isomers. Same molecular formula, different connectivity. All right. So here we have a bridged bicyclic. How many, pardon me, I just slammed down my dinner before I started doing this. How many stereoisomers for the following compound? So the answer to this question, we know that the number of stereoisomers is what? 2 to the n. Don't worry, I'm not going to trick you on this question and give you a meso compound. It will not be meso at all. All right. So what we're going to do is we're going to find. Okay, so again, if I give you something like this, it's not going to be a meso. You need to find the number of stereogenic centers. So just, I'm randomly starting here. Here's 1. Okay. There's obviously no symmetry in this compound. And coming off that pink carbon are what, 4 different groups because there's a hydrogen implied. Same thing here. This is my so-called bridgehead carbon. Okay. Even though there's an oxygen up here, this green carbon is 2 bonds away from the oxygen, and this purple carbon is directly attached to the oxygen. Okay, these other carbons, okay, this is a CH2, this is a CH2, okay, this is sp2, so it can't be chiral, so I have 2 to the 3 stereoisomers, or 8. Okay, now you will have a question like both of these. Okay, so also assigning R and S. You do not need to name this compound because frankly, I would have to struggle to name this compound again. Okay, how many stereogenic centers do you have? You have 1 here. You have 1 here. And that's it. I almost tricked myself. This is not a stereogenic center here because why? Okay, and if it helps you, add in your methyls. Okay, if it helps you, add in your methyls. Actually, that's not a stereogenic center. So there's only 1. Well, that was not my intention, folks. That's crazy. Oh, well, it's going to be more than 1 on the exam. Does everybody see what I just saw? This is an isopropyl, and this is an isopropyl. So I almost double tricked myself. All right. So again, that's cool because this one right here is pretty complicated. Okay. I'm going to go ahead and I'm going to draw my hydrogen, and I know that's going to have the last priority. Okay. And just right off the bat, I can see that this methyl is going to have 3rd priority. I'm not going to go over why right now. Okay. And so what we're going to do is we're going to start at the stereogenic center, and we're going to go out until we can find a difference. Okay. Now, this stereogenic center right here, okay, is a tertiary carbon. Okay. This stereogenic center here is a secondary carbon. Now, they both are double bonded. All right. So we would pretend to break that double bond and add another carbon for assigning absolute configuration. But we don't really need to do that because automatically we can see that this being a tertiary carbon and this one being a secondary carbon gives this one on the left highest priority. This one, circle all of them, 2nd priority. And again, I like to bring my stuff down and reassign it counterclockwise, but the hydrogen is coming out. So I'm going to flip it around and say that this is an R absolute configuration. Sorry about those isopropyls, folks. See, even I have to stop and think sometimes. All right. Looking down the indicated bond, starting at the conformer I give you. So this is important. Some of you guys just start wherever the hell you want. Okay, can't do that. Right now, what we can see is the dihedral angle of these two methyl groups is 0 because they're in the same plane, right? So it has to be eclipsed. So I'm just going to go ahead and I'm going to draw those first. Okay. This methyl is coming out, so I'm going to rotate it this way. So this methyl right here, when I take it and I flip it, we'll put it here. Okay, the other thing is the implied hydrogen. Okay, the isopropyl group here, okay, is opposite of the methyl because the isopropyl is dashed and the purple methyl, okay, it's opposite the purple methyl or pink, I don't know, just not green. Okay, so I'm just going to label it isopropyl. And then, of course, there's another implied hydrogen there. So I'm just going to stick it here. All right. So we're actually starting in an eclipse formation. Okay. Actually starting in an eclipse formation. And so, again, there's a bunch of different ways to do this correctly. Okay. I am going to keep my front stationary and I'm going to rotate my back clockwise in 60-degree increments. Okay. And so I like to show the little dipsy doodle here. And so I'm going to copy and paste this. Actually, going to copy and paste it 4 times. And then I'm just going to erase the back and redraw it. I should have done that first. Oh, well, shit happens, right? Yeah, I really should have done that first. Okay, so the first one, my isopropyl is now in the 12 o'clock position. IPR. Okay, that blue hydrogen that was in the back is now here. Okay, and the methyl is now gouged to the bottom methyl. I'm going to do another rotation. Again, going and erasing all the stuff in the back. So based on the staggered conformer I just drew, okay, this hydrogen methyl is now eclipsing. This methyl hydrogen is now eclipsing, my bad. And then over here, we have an isopropyl methyl eclipsing. I'm going to do another 60-degree rotation in the back, keeping again the front consistent. And again, based on the eclipsed conformer I just drew, now this isopropyl group is going to be gouged to the bottom. Oops, I didn't completely erase that, my bad. It's going to be gouged to, actually now, both of these methyls. The blue H that was in the 6 o'clock position is now in the, I guess that would be what, 8 o'clock position. And the green methyl that was in the 10 o'clock position is now in the 12 o'clock position. And so now, based on what I have to draw a relative energy diagram. Okay. And so this is going to look very different from the ones I showed you in class. Because why? Okay, first of all, we're starting with a high energy conformer. Okay, but that's not the highest energy conformer. This methyl isopropyl eclipsing is going to be a much larger interaction than this methyl-methyl eclipsing. So this is actually my highest energy conformer. Okay. This last conformer I drew, all of my big bulky R groups are what? They're all gouged to each other. Okay, so everything is gouged. Whereas here I have isopropyl methyl gouged and I have methyl-methyl gouged. But here I have methyl-methyl, methyl isopropyl, and isopropyl methyl. So all of these gouged interactions are going to make this last staggered conformer the highest energy staggered conformer. So the second conformer I drew is the lowest. This is going to be the second lowest. And the one I started off with in this case is going to be the second highest. Okay. And so all of your eclipsing conformers are always going to be higher in energy than any of your staggered conformers. The eclipse starts on the hills. In other words, like a mountain or a hill, Hill, not Heal. Okay, starts on the hill. And then you start high, then you go to the valley. Okay, that's going to be your staggered. And then you go up again. Okay, eclipse, and then you go back down to a valley. And I'll show you what I mean. I'm just going to randomly start here. And then I'll label the conformers. This is my third conformer. And that's my second conformer. Energy goes on the y-axis. This is going to be 0 degrees, 60-degree rotation, 120-degree rotation, 180. Okay. And so again, if I were to have you to label these A, B, C, and D, A and C, this is what I was just saying. Your eclipsing conformers are always going to be your hilltops. Okay, they're always going to be at the top of your peaks. Whereas your staggards are always going to be in your valleys. Okay, your staggards are always... Ah, shit. Yeah, I just saw it. For those of you that are pooping yourselves, really hard to draw this. My bad. I didn't draw the lowest as the lowest. Sorry if I just flipped you out. I am so sorry. So this is the highest. And this is the second lowest. My bad. There we go. Shit, now my numbering doesn't match. Oh, well, you know what I mean. This is why I always say the number after you draw your diagram. When I say number, I mean this axis. Okay? And by the way, labeling your axis is going to be worth 2 points. All right? And so you have to draw. Now, again, you can spin the front. You can spin the back counterclockwise. And whatever you draw, it has to match your energy diagram. And so it's kind of a pain in the ass to draw, or to grade rather, because there's more than one way to answer this correctly. But, you know, unfortunately, there's hundreds of thousands of ways to answer it incorrectly. All righty. Oh, that was fun. All right. So now we're going to convert this Newman projection to a chair, and then we're going to do a ring flip. So this carbon-carbon bond is this carbon-carbon bond. This carbon in the front going up is this carbon in the front going up. Okay, so I'm saying we're looking down these two carbon-carbon bonds. This carbon in the front and the one in the back is right here. And then this blue carbon down here pointing down is that carbon here. Okay, so there's nothing on the front carbon to the left. And so I'm going to just start filling out my substituents. This ethyl bromine are both on the back carbon. Be careful to draw correctly. Okay. If my axial is up, then my equatorial needs to be down. And remember, the angle of this, well, it's kind of close, but not really. The angle of this needs to match the angle 2 over. Again, that's why I'm providing you chairs, so you can get your angles correct. Okay, I'm never going to give you anything on the middle because you can't tell. Back here, okay, this methyl's on the back carbon here. Oops. And then this OH is on the front carbon, equatorial. And again, this bond here is going to dictate the slope of this bond here. All right. So then we're going to do a ring flip. Okay. And so I'm a clockwise kind of girl. So I'm going to shift everything over one spot. So my ethyl is up over here. It's up axial. So it needs to remain up, but equatorial. Bromine is down equatorial, so it's going to go down axial here. Paying attention, 1, but you can't see that. Paying attention to There we go. 1, 2, 3 carbons away is my methyl. This methyl right here is up axial, so it's going to shift over here to up equatorial. Oops. The OH is up equatorial, so it's now going to be here, up axial. Show the equilibrium. Okay, so we're going to ignore these two small groups here, concentrating only on the alkyl groups. And so the bulkier the alkyl group, the more we want it, okay, in the so-called what? Equatorial position to alleviate the 1,3 diaxial interactions. Okay, and so the equilibrium is going to favor my ethyl in equatorial. So you draw your equilibrium arrows like that. Okay. If you don't draw the right chair, you can't get partial credit for equilibrium. Sorry, it's just the way it is. Okay, it's just the way it is. Alrighty, moving on. Below are 2 or 4 isomeric dimethyl cyclopentanes. Okay, answer the following questions. How are the compounds each related to each other? Well, all I have to do is take B and rotate it about 30 degrees. Okay, just rotate it counterclockwise 30 degrees, and I can see that B will then be a mirror image of A. Again, we can do this the same way we've been doing it. I can assign this wedge priorities. So 1, 2, 3. Okay, so it is what? It's an R. Go over here. Same thing, 1, 2, 3. This is an S. Go over here. 1, 2, 3. They are counterclockwise, but it's going behind. My hydrogen is poking out the wrong direction. So it is an R. Same thing over here. 1, 2, 3. Everything is counterclockwise. Okay. But again, flipping it, I'm sorry, everything is clockwise. My bad. Okay. And so this is S. So I have an RR and I have an SS. So A and B are what? By definition, they are enantiomers. A and C are what? Okay. They're not they're constitutional isomers, right? Because A has 1,3 dimethyl and C is what? 1,1 dimethyl. Okay. So if you're not sure, you can always name them. Okay. So these are constitutional isomers, CI. A and D, well, B is trans, D is cis. Can't be mirror images, right? So then they have to be what? Diastereomers. Okay, and then A and D, well, if A and B are enantiomers and B and D are diastereomers, then by definition, A and D must also be diastereomers. It's like, isn't it amazing how many new words you've learned this semester? Good Lord, if you would have been listening to this video like 6 weeks ago, you would have been like, what's wrong with that crazy woman? All right. Under each of these, label if they're optically active. Okay. And so A and B are chiral. Why? What I was telling you about before. The R is going to have an optical rotation. The other R is going to have an optical rotation. So they'll add to each other. S and S, same thing, just opposite. C is achiral. Okay, why? Well, I could never sign an absolute configuration, right? D is what? Okay, it's a meso compound. Okay, so it's achiral. So which compounds would be optically active? A and B. Which compounds have a plane of symmetry? C and D. Okay. Okay, what about the boiling points? Now remember, in enantiomers, everything's the same except an optical rotation. So A and B would have what? The same boiling points. B and C would have what? Different. Have no idea what they would be, but we know that they would be different. B and D would also be different. And my meso compound is D. Okay? All right. Moving on. Identify any strain that's present. All right? The following new ones. Okay, right off the bat, we see that my ethyl and methyl are gauche. Gauche is not a strain. A gauche is a relative position. Okay? And so we don't list gauche as a strain. Gauche is a type of steric strain. So everything else has a dihedral angle of 60 degrees. OH and H, we don't talk about hydrogens being gauche with anything because it doesn't matter. So sterics. Okay. Over here, okay, we've done a rotation. These guys are eclipsing. Okay. Everything's eclipsing. So if everything is eclipsing, even hydrogens, I know that I have what? Torsional strain. Okay. And I do have what? The methyl ethyl is also giving me steric. If I were to give you cyclobutane, what would you have? Angle. Okay. Don't worry about cyclobutane. I'm just reviewing you. And what if I were to give you this chair conformer like this? How much? What strain? Okay, so it's a type of gauche, but what do we call this? 1,3-diaxial. What if I were to give you this chair conformer? What type of strain? None. Okay, because everything is staggered. Okay, so none is also an acceptable answer for this. All right. Oh, moving on to spectroscopy. Yay for spectroscopy. How many proton signals does each compound have? Well, 1, 2, 3, 4, 5, 6. Okay. So this is hexane. So my two terminal methyls would be the same. The second N would be the same. And the third N would be the same. So I'd have a grand total of how many unique signals? Well, again, because of symmetry. Now I drew this weird in a weird conformation. Okay. But I would have only 6 signals. Signals are the number of unique hydrogens, they're not the number of hydrogens. Okay. Going over to this ester, these two hydrogens are the same. This CH2 and this CH2 is the same. This terminal methyl are the same. So this would have 3. Boy, I sure was in a symmetrical mood when I was making this exam, wasn't I? Jesus. This is called pyrrole. Don't forget to count the hydrogen coming off the nitrogen. That's its own signal. This hydrogen and this hydrogen are the same. Again, pyrrole is pyrrole. And then this hydrogen are the same. Apparently, I also had 3 on the brain. Now we're going to break it up a little bit. This is an isopropyl group. Again, we have free rotation. So those two CH3s are the same. The CH is unique. The CH2 is unique. The CH2 is unique. And this CH3 on this side is its own signal. Okay. So counting up the numbers, I have 1, 2, 3, 4, 5. 5 signals. All right, I'm going to teach you something called 2 degrees of unsaturation. I'm going to teach you something called unsaturation. But basically, for every 1 degree of unsaturation, this equals 2 hydrogens. And so this comes back to that formula here. CN, H, 2N plus 2. So this is for saturated. So 0 degrees of unsaturation. And so I'm going to show you how to solve for this when I show you this. Okay. This is a carbon NMR. We'll talk about this on Tuesday. I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 carbons, because every carbon has its own unique signal, and there's no splitting. Okay, there's no splitting in carbon NMR. And again, we'll talk about this more on Tuesday. So if I was completely saturated, I would have what? Hydrogens would be equal to what? 2n plus 2, so 16 plus 2 would be 18. But for every 1 degree of unsaturation, I'm going to remove 2 hydrogens. So this is 4. So the answer is CHH14. Okay. We have no idea what this molecule is. Okay. But I did tell you it was a hydrocarbon, and I told you there were 2 degrees of unsaturation. So at least we know its molecular formula. We have no idea. Okay, we have no idea. It could be a diene, it could be 2 rings, it could be a ring with a double bond. We have no idea, but at least we have its molecular formula. Okay? Keep wanting to ask if there's questions. All right, we're going to go over this too. These are very big. So I either will ask you this on the exam, or I'll give you an NMR where this is part of the answer. And knowing these splitting patterns. Okay. The first splitting pattern are 2 doublets. Okay. The only time you're ever going to have 2 doublets is with para substitution. And so this first one belongs to B. The second one, I gave you a hint here. I told you there was a singlet. The only time you're going to have a singlet if you have a what? A meta substituted benzene derivative. Okay. So this is meta. So meta is single. So this would be A. Then by definition, or by process of elimination, the only thing that's left here is C. And sometimes that's what I'm going to ask you to do. Okay. I'm going to give you information where you can solve all of them but one, and then by process of elimination, whatever's left must be it. Moving forward. So this is what I was talking about in class when we were going over mass spectra. Okay. Obviously, this is a 3 to 1 ratio. This is chlorine. This is an odd number. This is nitrogen. This is an M and an M plus 2, but it's 1 to 1. So this is bromine. This is even. So all we know is it's what? It's not nitrated. Okay. There's no M plus 2 peak, so it can't be chlorine or bromine. And so that's it. Okay. The first peak is chlorinated, so it belongs to B. The second peak is nitrated, so it belongs to C. The last peak is brominated, so it belongs to A. And then the last one that's left must be D. That's it. That's all you need to know. I believe that's all you need to know for the MCAT too. So you're welcome. Yeah, sorry about the formatting here. Sometimes converting is a pain in the ass. Okay, again, this is matching. Figure out what it is and then go forward. Do one at a time. Everybody knows what an alcohol looks like, and so let's go find our alcohol. Oh, gee, this is our alcohol. This must be E. Boom. Okay. What else do we want to know here? Well, we know that this secondary amine is going to have what? A fang. A fang. And I remember giving this exam. A lot of these students thought that this was a fang and this was a fang. No. You see how you have this, it's what's called an overtone here. Okay. That's indicative of an NH or an OH peak. Sometimes. And so this is my NH peak right here. Everything else is pointless. D. So let's go back to this first one. What is this? Well, I have this guy right here at about 2100. I have this guy here at about 3300. And so I know that I must have a terminal alkyne. So this is A. Okay. This one right here, I'm really not sure what it is, so I'm just going to skip it. But what I do see here is I see what? A big fat carbonyl. Okay. And over here, I see a big fat carbonyl. I go back over here to my unknowns, and I have 2 carbonyl compounds. Carboxylic acid, okay? And then I have this aldehyde. And you're like, huh, aldehydes. She said something about aldehydes. Well, you remember that peak at about 2700 that I pointed out? That's right here. That's that so-called shouldering. You're like, how am I supposed to know that? Some of this does require recognizing patterns. Okay. This is a C. Now, you're like, well, how am I not supposed to know what this is? On the exam, you have my permission to ask me if this is a thing or not. I will tell you whether or not it's a thing. If I look at you like you're an idiot, that means it's probably something more like this. I don't know how else to say that. I'll come up with a better way to answer this question when the exam comes. I have almost a week. Okay. And so the other carbonyl, okay, this is the carboxylic acid OH, right? And so remember, I told you guys sometimes this can get buried under information. So that's my carboxylic acid OH. So that's going to be F. My aldehyde was what? C. I already labeled it. And then by process of elimination, B must be the only one that's left. Simple. Well, to me, you'll get there. All right. So the last thing, again, I apologize for this stupidness. So the last thing is you're going to have a question like this. You're going to have 2 NMR problems where you have to figure out the structure. And so one of them is just like this. Okay. I'm going to give you a molecular formula. And so X in this case is either bromine or chlorine. And if you don't write bromine or chlorine on your final structure, you're going to get points off. Again, this is a 1-to-1 ratio. So we know my molecular formula is C8H9Br. Not a whole lot of interesting stuff on the IR. It doesn't look like. It looks like everything. Well, let me see what my degrees of unsaturation are. Okay. My degrees of unsaturation are, so this is 2N plus 2, where N is the number of hydrogen carbons, minus X. I'm sorry, minus X or H's. Okay. And so I have 8 times 2 plus 2 is 16, 18, minus 9, minus 1. We're just going to make that a 10 because some of you guys are freaking out because of negative numbers. Because, oh my gosh. And so this gives me 8. Oh, so all this divided by 2 gives me 4 degrees of unsaturation. As I'm going to tell you next time, if I give you 4 degrees of unsaturation or more, probably you have a benzene ring because you have 1 ring, 1 degree of unsaturation, 3 bonds, 3 more degrees of unsaturation, for a total of 4. And so what's really interesting here is what? Nothing. I have sp3 carbon hydrogen stretching. I have sp2. Now that I know I have a benzene ring, I can figure out probably this is carbon-carbon aromatic, right? It's right around 1600. But who knows? This IR is not really useful. I mean, I had to do some calculations before I could get stuff out of this IR. Okay. So I'm looking at this and I'm looking at my substitution pattern. Oh, look, it is a benzene ring. Oh, wow. I was right with my 4 degrees of unsaturation. I have that singlet. And so I know that I have what? Let me not use X. Let me use Y because I don't want X to be confused. So I have a meta-substituted species. Okay, and that's it. That's all you're going to get out of these aromatic splitting patterns. We don't teach you guys what to do with those until you take our advanced NMR spectroscopy class, like I'm sure all of you guys are dying to take. Okay, and then Y and Z or whatever that's coming off this ring. Okay, and so I have a triplet that's 3 hydrogens. A triplet means it's what? Next to 2. Then I have a CH2 that's a quartet that's next to a CH3. That's it. These are the only signals. So what I know is that this is probably an ethyl group coming off my ring. And something I used to do, now this is not a very complicated NMR. All right. But some of them will be. And so something I would do is I would take my molecular formula, C8H89Br. So C8H9Br. And I would take what I've already figured out and I'd say, okay, I have 1, 2, 3, 4, 5, 6, 7, 8 carbons. I have 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens. And so the only thing that's left is the bromine. So then Y must be the bromine. I'm going to erase these. Now don't leave them like that because that makes it look like they're methyls. So to make it all nice and neat, I have meta ethyl bromo benzene. And that's it. Okie dokie.